In this video, we're going to discuss how to find the absolute maximum of a function on a specified interval. So this is a little bit different than what we've talked about already, which is finding local extrema or local maxima or local minima on a particular interval. And for that, we've used the first derivative test. So we're going to start off here with the definition of absolute maximum and minimum of a function on a specified interval. So f of c is called an absolute maximum of f if f of x is greater than or equal, if f of c is greater than or equal to f of x for all x in the domain of f. So you'll notice here that an absolute maximum is a y value. It's a y value that occurs at a particular x value. So a lot of times in the homework, things like that, they'll ask you to write your absolute maxima or minima as an ordered pair. But keep in mind that if they ask for an absolute maximum, it's a y value. It just happens to occur at a particular x value. So the definition of an absolute minimum is similar. The only difference is that the inequality has been flipped around here. So let's contrast absolute maxima and minima to local maxima and minima. So if you look at the graph of just this random function here, this point on the top of the left-hand peak here is it is a local maximum. That is, relatively speaking, like around that point, that's the highest point on the graph. But of course, there's a higher point on the graph, and it's over on the peak to the right. So the point at the top of that peak, the y value there is both a local and the global maximum of this function on its domain here. So a couple synonyms that may be used here. Sometimes people say local as relative minimum, so you'll hear local minima or maxima, relative minima and maxima. And in a similar way, global maxima or minima and absolute maxima and minima are used synonymously and interchangeably. So together, if we look at maxima and minima, we call that extrema, and that's a plural. So if you're just looking for a singular form of that word, it's extremum. Maximum, minimum are singular, maxima, minima are plural. The extreme value theorem is what we're going to cover next, and basically it tells us when we can be assured that we have both an absolute maximum and an absolute minimum of a function. So in this particular case, in our book, it's theorem 1. A function f is continuous on a function f that is continuous on a closed interval from a to b has both an absolute maximum value and an absolute minimum value on that closed interval. So you'll notice a few things about this. You need both continuity and a closed interval on which to work here. So our closed interval, notice the brackets on the ends of that interval there, so we include the endpoints. But we also need that the function is continuous. If you don't have both of these antecedents or these conditions, there's no guarantee that you'll have any absolute maxima or minima. So this theorem is going to give us a way to find absolute maxima and minima of a function on a closed interval. So absolute extrema, if they exist, must always occur at a critical value or possibly at an endpoint of a closed interval. So basically the technique is this. First, we're going to check to make sure that f is continuous on a closed interval from a to b. So basically what this first condition ensures is that the extreme value theorem applies. In other words, there is definitely an absolute maximum and an absolute minimum for us to go and find. So step 2 here is to find the critical values on the open interval from a to b. Step 3, take those critical values and the endpoints and plug them back into the function. Finally, step D, the absolute maximum of the function on this closed interval from a to b is the largest of the values that you found in the last step. And finally, part E, the absolute minimum of the function on the closed interval from a to b is the smallest value that you found in step C. So together, these steps are sometimes called the closed interval method. And the reason that we call this the closed interval method, of course, is because it only works when you have a closed interval on which to work and a continuous function on that closed interval. Both these conditions are very important for this technique to work. So let's put this technique to work in an example. So in this example, we want to find the absolute extrema of the function f of x equals x cubed minus 12x on the closed interval from -5 to 5 in part A, and in part B, the closed interval from -3 to 1. So we're going to apply the closed interval method step by step here. We'll go through part A in this video. You should try part B, and then when you come to class, we'll go over part B in lecture. So here's the solution for part A. So first of all, note that f of x is a polynomial function, and as a result, it's continuous on its entire domain, which is the entire real number line from -infinity to infinity. In particular, f of x is continuous on the closed interval from -5 to 5, which is the interval in question in part A. So checking these two conditions, namely that we have continuity and that we have a closed interval on which to work, are the conditions that are laid out to make sure that the extreme value theorem applies. In other words, that absolute extrema exist in this particular case. So now we're going to go on to part B, and for that we need to find critical numbers. And of course, to find critical numbers or critical values, we need to take a derivative. So the derivative of f of x in this case, f prime of x, is 3x squared minus 12. Next up, we set this equal to 0 and we solve for x. This is a very straightforward quadratic. Subtract 12 from, add 12 to both sides, divide by 3, take square roots, don't forget your plus and minus, and you'll find that x equals plus and minus 2. Now, both of these critical values lie in our closed interval. So in particular, we need to worry about both plus 2 and minus 2 in this particular case. So that takes care of part B. We found the critical values here. And both of them lie in the open interval from -5 to 5. Next up, we're going to evaluate f at the critical numbers, namely 2 and minus 2, as well as the endpoints of our closed interval, 5 and -5. So we're going to take these values and we're going to plug them all the way back into the original function, and this is going to complete part C. So we're going to take these values, plug them all the way back into the original function, and find the y values, in this case corresponding to 2, -2, 5, and -5. So f of 2 is -16. F of minus 2 is also positive 16. F of minus 5 is -65, and f of 5 is positive 65. So what we've done here is completed part C. Next up, for part D, we're going to find the largest of these y values, and in this particular case, it's 65. So 65 is our absolute maximum. On the other hand, -65 is the absolute minimum because it's the smallest y value that appears here. So this is parts D and E respectively. So now we'll go ahead and write our solution. So let's clear ourselves some room. So the absolute maximum of the function f of x on the closed interval from -5 is 65. Notice this is a y value and it occurs at the x value x equals 5. The absolute minimum, on the other hand, is -65. Once again, a y value that occurs at the x value x equals -5. So at this point, go ahead and give part B a shot. Keep your notes with you, bring them to class, and we'll go through part B in class. So next up, we're going to talk about a different technique for finding an absolute maximum, and that technique is called the second derivative test. So in this case, we're going to let f be continuous on an interval I, and we're going to assume that f has only one critical number or one critical value, c, in I. So in the first case here, if that critical value is a place at which the first derivative is 0, that is a place at which we have a horizontal tangent line, and we have sort of concave up behavior in our function at that point, then the value f of c is an absolute minimum of f on this interval I. So the basic idea here is that if you have a concave up function, you have this upward facing u, and the critical number in there where we have this horizontal tangent line therefore is going to be a minimum. On the other hand, if we have concave down at our single critical number on this interval, then we have something like an upside down U shape, in which case we have an absolute maximum at that critical number. So, a couple things to make sure of here. Be sure that you check that f is continuous on the interval in question, and that you have exactly one critical value on that interval. If both these conditions are not true, then there's no guarantee that the second derivative test will work. Now there's a drawback of the second derivative test that you need to be aware of.
And that's that if f double prime of c is 0, then the second derivative test tells you nothing at all. In other words, it fails. It doesn't tell you any information. So if you have a point at which your second derivative is 0 and your first derivative is 0 at x equals c, you have no information and you have to work with some other theorem. This is the second derivative test for global extrema, that is for global maxima and global minima. So there's also a second derivative test for local extrema, and the basic idea is the same. Really the only difference is you no longer have to check that you only have one critical number in your interval. So if you're only worried about local extrema, that condition doesn't really matter so much.
So let's take a look at an example of applying the second derivative test for global extrema. So in this example, we want to find the absolute or global extrema of the following two functions. In part A, f of x is 12 minus x minus 5 over x. And in part B, f of x equals 5 ln of x minus x. And in both of these cases, we want to examine these functions for absolute extrema on the open interval from 0 to infinity. So the first thing that you'll notice here is this is not a closed interval. What that means is that the closed interval method is not going to apply. So essentially, we're forced into using the second derivative test here. So we're going to start this one, first of all, by noting that f of x is continuous on its domain. It's in part A. So what we have here is a rational function. It's continuous on its domain. In particular, we're continuous on the open interval 0 to infinity, which is the open interval that we're concerned about here. So we're going to write f of x using negative exponents. So in that very last term, we slide that x on the bottom up to the top, where we make its exponent -1, and then we can apply a simple power rule to take the derivative. F prime of x equals -1 plus 5x to the -2. Next up, we're going to find the critical values of f on the open interval from 0 to infinity. Now you'll notice that we have two ways in which a critical number can appear. A place at which the derivative is undefined and places at which the derivative is 0. The first of which, that is places at which the derivative is undefined, occurs at x equals 0 here, but that's outside of the interval that we're concerned about, so we're not too worried about that. So what we're going to do now is set f prime of x equal to 0 and solve for x. So what we have is a rational equation, and the easiest way to solve that is by multiplying both sides by the LCD, which is x squared in this case. And when you do that and move the x squared over, what you'll end up with is x squared equals 5. Take the square root of both sides to get x equals plus or minus root 5. These are the two critical numbers of f, but you'll notice here that we have one too many. But in this particular case, we're not worried about the negative here. Because we're working with the open interval from 0 to infinity, that is strictly positive numbers, we throw away the negative sign. We're not concerned about it in this particular example. So the next step, we need to take a look at the second derivative. And once again, for that, we can apply the power rule to f prime of x equals -1 plus 5x to the -2. And what we'll get is f double prime of x is -10 all divided by x cubed. Now, what we're interested in is f double prime at the critical number root 5. So we take that critical number and we plug it into the second derivative. And what we end up with is -10 over quantity, root 5 cubed. I don't really care so much about what that number is. I just care that it's less than 0. That is, I just care that it's negative. So once we note that, we have concave down. And that indicates that we have an absolute maximum at our single critical value, root 5 here. So we're going to take that root 5 and plug it back into the original function. So what we end up with is f of root 5 is 12 minus root 5 minus 5 over root 5. Now that last term, 5 over root 5, simplifies to just root 5. So this is going back, way back to when you were rationalizing denominators. But in the end, what you get is 5 to the first over 5 to the 1/2. Subtract exponents, you get 5 to the 1/2. Turn that into a radical, and that's root 5. So what we have here is that 12 minus 2 root 5 is the absolute maximum of this function on the open interval from 0 to infinity. And we get that because the second derivative test for global extrema applies. Keep in mind here, we checked f is continuous. We only have a single critical number on the interval that we're concerned about. So you can think of this as restricting the domain of f to just positive numbers, and that's all we're worried about in this case. So at this point, go ahead and take a shot at part B. Keep your notes, bring them to class, and we'll go through part B in class together. That concludes the video on finding absolute extrema of functions using the closed interval method and the second derivative test for global extrema.